Hello my dear warriors, welcome aboard. This is Captain Shreyas here, your physics master teacher on the channel. And over the past decade or so, whatever experience I have gathered training, coaching kids, sending them to the top-notch institutes, I'm going to use that experience for you guys in the Fast Track series in this precise, concise lectures where you're going to get all the important mind maps, formulas, concepts, the theory part as well as the graphical part in these theory lectures. So these are short and crisp lectures like you can see even in the title, and there will be separate live problem solving sessions. So guys, the reason for recording these classes is so that I can be precise, concise and to the point, and you can use this again and again for revision. I hope you have smashed the like button. If you have not done that, do that right now, and what are you waiting for? Go hit the subscribe button as well. So today I'm going to tell you all about basically atoms, wave particle duality, photons and photoelectric effect. Let's start with atoms first. We all know everything around us is made up of matter, and matter is made up of particles, and the particles are made up of smaller particles, and if you keep on dividing that, you get the smallest particle. Well, that's what people believed long time back. Those were called as atoms. But then it was further discovered that the atoms are also made up of subatomic particles which are even tinier than the atoms themselves. So Thomson discovered the electron, which is negatively charged, very small mass. Then Rutherford discovered the proton, which has positive charge and a decent amount of mass as compared to the electron. And Chadwick discovered nothing but the neutron, which has neutral charge, almost the same mass as that of the proton. Now, there were many theories of atoms, like the atom looks like that, like this. So each theory overcame the flaws of the previous theory. So we need to know few of those theories and their limitations and what they proposed. Let's start with Dalton's theory. So according to Dalton, every matter is made up of teeny weeny particles. What is it called? It's called atoms. Perfect. All atoms of an element, let's say sulfur or oxygen, they are identical. Yes, atom of oxygen anywhere will be identical in mass, size and other properties. But if you take oxygen with carbon, they will be different in mass, size as well as their properties. Also, he said that you cannot create or destroy atoms and you cannot divide the atoms into smaller particles. Well, that was not true. We know that atoms can be further divided into smaller particles. In fact, that also becomes the limitation. Atoms of different elements can combine with each other in fixed whole numbers. That makes sense. Like if you have to make a water molecule, then you need 2 hydrogens and 1 oxygen. You cannot have 1.5 hydrogen and 2.5 oxygen. That doesn't make sense. So you have to have it in fixed whole number values only. Also, in chemical reactions, these atoms can be rearranged. So you have some chemical reacting with some other chemical. These atoms might get exchanged, might get rearranged, and you might get newer compounds on the other side. So most of the things it could predict properly, but there were some limitations to Dalton's theory, like you can see. That was overcome by none other than Thomson. Thomson was able to explain how conduction of electricity happens. And they knew at that point of time that when electricity flows, it's the electrons that move, and electrons are negatively charged. In fact, Thomson was the discoverer of electrons. So he suggested and proposed that atoms are like a watermelon. The red part being the positive charge. It's like the positive charge is distributed everywhere in the space of the atom, and these teeny mini particles, which are like those seeds of the watermelon, are negative charges. So when you apply a battery's voltage difference, the voltage difference propels these electrons, pushes these electrons, and that's how the conduction of electricity happens. These particles being small, they are easy to flow, and that's why the electrons are mobilized. And he also said that the total charge of the atom is 0, because even though the electrons are teeny weeny and the gel of positive charge is spread everywhere, the total charge positive and the total charge negative is equal. So atoms are electrically neutral, which is correct. But there were some limitations, like it could not explain why there are spectral lines. So whenever you take elements, you will see that there are some kind of spectral lines which come out, which are unique to that element. He could not explain that. He could not also explain why the alpha particles get scattered, which was explained by Rutherford. So these were the major limitations of, Thomson. So then Rutherford comes and he does a famous gold foil experiment which is bombarded by alpha particles. Alpha particles are nothing but positively charged particles. It's helium nucleus without the electrons. So 2 protons and 2 neutrons. Now, when these positive particles, that's alpha particles, are bombarded on the gold foil, it was found most of them pass through the sheet. Very few get deflected by small angles, very few get deflected by a very large angle. Because most of them pass through it undeviated, that means most of the atom is empty. That's why it's going undeviated. Very few of them got deflected, most likely because of the positive charge of the nucleus, which is there at the center, and that's why it got deflected. A very few which went head on onto the nucleus, they will get repelled and they will make a U-turn and they will get deflected by a very large angle. So he said that the positive charge is concentrated. It has almost all the mass of the atom concentrated at that particular location that he called as the nucleus. And he said the nucleus contains the positive charge, and the electrons which are negative charge do not fall onto the nucleus even though there is attractive force, because they are revolving. Just like the earth revolves around the sun by taking help of the gravitational force, he proposed that the electrons also revolve just like the planets around the sun, making use of the electric force as the centripetal force. This was fine, but there were limitations of that too. So he could not explain that if the electrons are revolving, that means they are accelerated charges, and accelerated charges should emit radiation. And if they emit radiation, they lose energy and they should fall into the nucleus. That's it, that's the end of the atom. But that's not what happens. So he could not explain why the electrons, even though they are accelerated particles, why they don't emit radiation. He could not also explain that if the electron can revolve around the nucleus in any orbit possible, that means it could have hypothetically any possible energy. So when electron changes the orbit, it could change the energy and it will emit or absorb any kind of radiation. So all possible wavelengths should be emitted by the electron transitions. But that's not what is found. You only get fixed amount of wavelengths. So you could not explain why you get only fixed wavelengths, why there is no continuous energy. He could not explain that. These limitations were overcome obviously by none other than Bohr's model of atom. So Bohr proposed, like whatever you guys said, most of it is correct, but there is something more to it. First one, the electron in an atom can revolve only in certain orbits without the emission of radiant energy. In fact, these orbits are called as the stable orbits or stationary orbits. In these stationary orbits, the electron maintains its energy and it does not emit any kind of radiation. The explanation details are not a part of JEE syllabus. That's something beyond the scope. But understand, he proposed that there are stationary orbits and only in those stationary orbits the electrons are stable and happy. The peculiarity is that the angular momentum of that electron revolving is integral multiple n times, that's integer, times h by 2 pi. H is Planck's constant by 2 pi. That is mvr, that's angular momentum, is nh by 2 pi, where n can be any integer, and we know that n also happens to be the principal quantum number. Also, he said that when an electron changes the orbit from lower to higher or higher to lower, there is some kind of energy involvement. So if it goes from lower to higher orbit, that means it's going to a higher energy state. It will absorb radiation or photon. So when it absorbs the photon, it jumps to higher energy state, and when it releases the energy, it jumps to a lower energy state. So according to him, it was the energy difference between the orbits which is equal to the energy of the photon which is emitted or absorbed, which is also equal to h times of f. F is the frequency and h is nothing but the Planck's constant. Now, using his postulates and Newtonian mechanics like F is equal to ma, acceleration is v square by r, and so on and so forth, he was able to derive the radius, the speed and energy of the electron in any orbit. Starting off with speed and radius, he found that the velocity is given by this formula, Obviously, you don't have to by heart this. The only thing you need to remember out here is that the velocity is directly proportional to z by n. Z is your atomic number, n is your principal quantum number. He also found that the radius of any orbit is directly proportional to n square by z. In fact, there is a constant of proportionality which you need to remember over here is 0.529 times of n square by z. This is only in Armstrong. This is also a very important relationship for finding the radius of any electron in any orbit. You can just put n is equal to 1, 2, 3 and you will get the speed or the radius in that particular orbit. For hydrogen, z will be 1. For helium, z will be 2, so on and so forth. That's the atomic number. He also found the energy of the electron in any shell or any orbit, and this was the formula, but again you are not going to remember that. The only thing you're going to remember is nothing but the energy in the nth shell or nth orbit will be minus 13.6, that's the constant of proportionality, into z square by n square, but this happens to be in electron volt because these energies are very, very small. So this is the thing that you will remember, not the one over there. Also keep this in mind that the kinetic energy, obviously the electron has kinetic energy of the electron, is equal to the negative of the total energy, and also the potential energy of the electron because of the electric force of attraction or repulsion is just nothing but 2 times of the energy, total energy of that electron. So this is also a very important thing which you should know because the total energy is the sum of kinetic and potential. Now let's talk about spectrum. You might have heard about absorption and emission spectrum. So let's understand what it actually means. We all know that electrons can only stay in stable orbits. They cannot be in between those stable orbits. And electrons can absorb or release the energy by absorbing the photon or releasing the photon. So imagine light being incident on a certain element. Then that light, which contains photons, will make sure that these electrons absorb them, and these electron jumps to any of the higher energy state. Maybe an electron might jump here or there or here, nothing in between. So there will be certain photons which get absorbed, certain photons which will not be absorbed because the electrons can't jump anywhere in between. They can be here, 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 here or here. Nothing in between. That's going to make it unstable. That's the reason why you will see missing wavelengths, because only certain wavelengths get absorbed by any element. The exact reverse also holds true. If you have lots of atoms and they have a lot of thermal energy, they collide and they can knock out those electrons, or those electrons might jump to higher energy states. When they jump to higher energy states and they again come back, they can come from here to here, here to here, here to here, but not from here to here, because that is not going to be a stable orbit. So when they jump down, they get de-excited, they release photons, and that comes out as the emission spectrum. So you can see emission spectrum is also very peculiar for every element. These are exactly those wavelengths which are emitted by the electron transition from higher energy to lower energy state. In fact, these things also have a name. The transitions have a name based on who discovered what. So all those transitions for a hydrogen atom which happen from any shell to the lowermost shell, which is n is equal to 1, which is the K shell. I hope you know this. This is a K shell, this is L, this is M, N, and so on and so forth. So the electron transits from any higher shell to the lowermost grounded state where n is equal to 1, or the K shell. It's called as the Lyman series. If the transition happens from any higher shell to n is equal to 2, then it's called Balmer. Then if it happens to n is equal to 3 from any higher shell, it's called Paschen, then bracket, P-fund, and so on and so forth. So these are the names given to the spectral lines based on the person discovering it. Also to keep in mind, this is called as the first line of Lyman series. This is the first line of Balmer series. This is the first line of Paschen series. The last line would be this one, actually from infinity. That means from a free electron to the ground state. That would be the last line of Lyman. The last line of Balmer will be from infinity to 2. For Paschen, it will be from infinity to 3. So as you go higher, the energy increases, and when n tends to infinity, then basically it's a free electron. It's no longer bound to the atom. Next up is the formula of the wavelength which is absorbed or emitted. So if the transition happens from N1 to N2, N1 to N2, N1 and N2 are two principal quantum numbers. The wavelength emitted is just given by this formula. 1 by wavelength is Rydberg's constant, atomic number square, 1 by N1 square minus 1 by N2 square. N1 and N2 are just the quantum numbers. Z is the atomic number. Rydberg constant is roughly 1.1 10 to the power 7. That gives you the reciprocal of the wavelength that's going to come out or that's going to be absorbed. That's a very important formula, the Rydberg's formula for electron transitions for getting the spectrum. Now, there are some limitations to Bohr's model as well. Like one of the first important limitation is that it could not explain Heisenberg's uncertainty, or it did not obey that. Like you can precisely locate the position as well as the momentum, which is not true according to Heisenberg's uncertainty. Also, the theory made very good predictions for small atom like hydrogen, but for larger atoms like helium, lithium, it failed. For bigger elements, it failed miserably. Also, it was not able to explain why those spectral lines which I just showed over here, these lines split into smaller lines when you apply magnetic field. So that was called as the Zeeman effect. You don't have to know what exactly Zeeman effect is, but you just need to know that when magnetic field was applied, then those lines split. Why does it happen? It was not able to explain. So there were more theories beyond that, but we limit ourselves to only Bohr's theory. So that was atomic structure for all of you. Moving ahead now to wave-particle duality. I hope you are enjoying the session and you have already smashed the like button. If you have not done that, do that, and also hit the subscribe button, guys. Now let's talk about dual behavior. I'm pretty sure you might have heard of dual personalities. So even particles and lights have dual behavior. So light is found to show particle-like behavior. In fact, experiments like the Crompton effect showed that light possesses particle nature as well. And theories like interference or diffraction showed that light has wave-like characteristics. Particles have certain properties, like they have momentum, they can hit something, they can collide with something. Waves have certain other properties, like they have amplitudes, they have wavelength, they have frequency, and they also can meet with each other, like interfere with each other, and so on and so forth. Light showed both the things, so that's why it's said to have dual nature, just like dual personality. So some experiments show this, some experiments show the other one. So we assume that light has dual nature depending on what experiment you are performing. So we're going to study both these behaviors. There is a separate chapter called light waves to study exclusively the wave nature of light. Now we will study more about the particle nature of light. The particle of light is called as the photon. In fact, light is a carrier of energy. This energy does not flow continuously, but in fact it flows in packets, small packets. These packets of energy is called as a photon, and each packet of photon basically has an energy equal to h into f, or just hc divided by lambda. F is frequency, c is speed of light, lambda is wavelength, h is your Planck's constant. The value of the Planck's constant roughly is 6.6 into 10 to the power minus 34 SI units. Now, there are more things about a photon which you should know. Like a photon always moves at the speed of light. That's very fast. 3 into 10 to the power 8 meters per second. And it is true no matter where you sit and make these observations. Also, the photon's energy, the photon is the energy of the particle, and it has no meaning. It has no meaning at rest. So you cannot see the photon at rest. Like you can see over here, photon always moves at the speed of light. So you can never see the photon at rest. Hence, the rest mass is just assumed for just theoretical purposes to be zero. Practically, nobody can see the photon at rest. Photons are neutral, they are stable, they do not carry charge, so they do not get deflected by electric or magnetic fields. and also there is momentum associated with photon, because remember photon is particle, so it should have momentum, and the momentum of the photon is just given by h by lambda, or you can just say it is energy of that photon divided by c. So either of the two formulas you can use for finding the momentum of the photon. Great. Moving ahead now is the force or the pressure which light exerts on any surface. When light falls on any surface, it applies a pressure because light possesses momentum, and when it hits the surface there is an impulse, there is a change in momentum which causes that force. If you measure that force per unit area, you get the pressure, which is called as the radiation pressure. Now depending on the nature of the surface, there are two formulas. If the surface absorbs the light, then the force acting on the particle is given by IA by C. If you shift that A below, force per unit area, you are just going to get the pressure, which is just going to be I by C. So this is very important formula. This is nothing but your radiation pressure. If the surface is absorbing, if it is reflecting, the incident photon will come back. The changes in the momentum are twice as of this. So the formula for the force will be 2IA by C, and formula for the radiation pressure is 2 times I by C, which is exactly double of the absorption case. The next important thing is basically de Broglie's hypothesis. Photon is the particle nature of light. So de Broglie thought, does matter which is there around us, which has mass, does that also have wave-like behavior? The answer for that is yes, and he gave the wavelength of all the matter around us. The wavelength of everything around you which has some mass and is moving is given by h by mv. The wavelength refers to the wave nature of the matter, which is then called as the matter wave. So matter wave is a very different kind of a wave. It's not like sound, it's not like wave on a string, or it's not even electromagnetic. It's something which you cannot probably see, but probably you can see only the effects of it when you conduct certain experiments. So that is the matter wave. If you rewrite mv in terms of kinetic energy, because kinetic energy is half times mv square, so you can get exactly the same expression. So wavelength also is h by root of 2 kinetic energy times the mass. This is the de Broglie's wavelength of a matter which is moving, also referred to as the matter wave's wavelength. Now, once we understand that, okay, light has dual nature and the particle nature is called photons. Photons have energy, photons have momentum. Can this momentum, apart from applying force and pressure, can it knock out certain things? The answer to that is yes, and that is precisely the photoelectric effect. So when light falls on a surface, apart from applying that pressure or the force, if it hits the atoms, and more precisely the electrons are small teeny weeny particles, and they are revolving in orbits. Maybe they can be just knocked out of those orbits and they can be set free. So when light of sufficiently high energy falls on a metallic surface, because they have very readily available electrons, those electrons get knocked out. That electron is called as photoelectron, because it is happening because of the light photo that resembles those words. That's why they are called photoelectrons, and this entire effect is called as the photoelectric effect. Generally, to study the photoelectric effect, you use this elaborate setup where you have an empty vacuum chamber. There is a glass tube and light is falling onto it through a window on a metallic surface. As the light falls, it has sufficient energy, then the electrons get thrown out. Those photoelectrons are then connected by the other side, which is the anode, and the electrons flow through the circuit and again fall back into the metallic surface. Again, new light will fall and eject those photoelectrons, and that's how the electrons keep on flowing in the circuit. And if you have an ammeter and voltmeter, you can measure how much current is there and how much voltage is there. You can do many things, like if you have a battery, you can support it or you can connect it in opposite direction. You can either help or assist the current, that's called as the forward bias, or you can connect the battery in the opposite direction of the current to stop the flow, that's called as the reverse bias. And you can see the effects of the battery voltage on the current. You can also study the effects of higher or lower intensity of light on the currents and the voltages. So all these things were done to finally give the photoelectric equation. Now, like I said, you need light of higher energy, because if the light has low energy, it might not be able to knock out that electron out of the shells or out of the atom. So there is a minimum frequency, because frequency decides the energy. So there is a minimum frequency of the light below which there is no photoelectric effect. There is a critical frequency after which the threshold frequency, that's what it is called, after which the photoelectric effect occurs. So there is a minimum energy requirement for the photoelectric effect to occur. That minimum energy is called as the work function. For different materials like aluminum, gold, copper, everyone will have different thresholds, different work functions, different energy to suck out that electron and throw it and eject it out as photoelectron. So the symbol for work function is pi, and it is nothing but the minimum energy of the photon, that will be h into f naught. You can also write it as hc by lambda naught. If f naught is threshold frequency, lambda naught will be threshold wavelength. So this is a very important formula, completely dependent on the material, nothing else. Now, like I said before, you can connect a battery to the photoelectric setup and see what are the effects out of that. If somebody connects the battery in forward bias, meaning helping the current, you will see these electrons which are thrown out of the metallic surface, they will get help, they will get assistance. That's why the current will increase. But after a point, even that current can't increase, because all the electrons ejected are reaching the other side safely. So there reaches a saturation point. So even after increasing the voltage beyond that point, you cannot see further increase in the current, because all the electrons are reaching the other side. The exact reverse also holds true. If you connect the battery in reverse bias, meaning you are applying the voltage opposite to the current's direction where it wants to flow, then these electrons are not sucked here. In fact, they are pushed or repelled back because of the reverse voltage, and not many electrons reach the other side. And if you keep on increasing the voltage, the current gradually falls down till it becomes zero. That voltage of the external source for which the current in the photoelectric effect stops is called as the stopping potential. Alright, so the maximum energy of the electron can be thus measured by the stopping potential, because these electrons have kinetic energy which is completely taken away by the reverse voltage. I can say that the kinetic energy gets converted into the electrical potential energy, and therefore the maximum kinetic energy of any electron in such a case will be E times of Vs, Vs being the stopping potential. Based on these observations, whatever I told you regarding the battery's voltage, you can also draw the graphs. Like you can see, if you apply forward voltage, the current slowly increases till it reaches saturation. If you apply reverse voltage, the current slowly decreases till it becomes zero, and that voltage is called stopping potential. You can also see one more thing, that if you increase the intensity of light, more photons will fall, more electrons will come out, more current will flow in the circuit. So current is directly proportional to the intensity of light. So you can see the graph shifts upper as you increase the intensity. But you have to see one interesting thing: no matter what the intensity of light is, the stopping potential is the same, because even if you increase the intensity of light, the energy of the photon does not increase, because energy of the photon is dependent on its frequency, hf. So increasing the intensity just increases the number of electrons, but not the energy of the photon. So that's why you will see that the electrons which come out are not of higher energy when you increase intensity. It will be of the same energy, but just more in quantity. That's all. That's why the stopping potential remains the same. Now Einstein, looking at all these things, he gave a very splendid equation which is called as the photoelectric equation, for which he won the Nobel Prize. And he also saw that when you have higher frequency, like blue light or violet light has higher frequency than green and higher frequency than red, then the electrons which come out are also of higher energy. So this made him understand that, okay, I can just use energy principle and give the famous photoelectric equation. So the photoelectric equation is nothing but energy of the photon, which is falling, gets partially utilized in sucking that electron out of that atom. That means the work function, plus the remaining part is there as the kinetic energy. So energy of the photon is utilized in taking that out, so work function, and the remaining part is going as the kinetic energy. If you want, you can also write this as HF is equal to HF naught, and kinetic energy is nothing but E times of Vs. So this is also another way of writing the equation. Some books use the symbol V, but I would avoid the symbol V because it might lead to confusion with the speed of the electron. So that was photoelectric effect and wave particle duality as well as atoms, and I'm pretty sure you enjoyed this session and learned a lot and revised all the concepts. The entire PDF will be available in the Telegram channel. Make sure you join it ASAP. And do not forget to smash the like button and also hit the subscribe button and leave your comments below on how you enjoyed this and what lecture you want next. Thank you so much. This was Captain Shreyas here, and I will be signing off. Hasta la vista.